So we're going to take a look here. SPECTRE, which is the name chosen by those who discovered it, and it comes from speculative execution of code. Now we're going to talk about in our CPU, we have some kinds of machine instructions that we've used as an example previously. We'll say move register R1, value C, move R2, and so that's actually a 1 there, and we'll say that's a value of 3, and we're going to have a number of instructions down here followed by some kind of jump instruction to do something else. Now, to understand how this works, we need to take a look at a part of a CPU known as an instruction pipeline. I'll write this out here. And the idea behind the pipeline is that we don't normally, in modern fast processors, run a single instruction at a time. So we may be thinking we have our CPU box here and it does one instruction. When that instruction is done, it goes on to the next one and the next one and so on. However, in a modern CPU, we actually operate on many instructions at once. You already saw the idea of a fetch, decode, execute cycle, and that provides an easy way to split our pipeline into 3 sections where we could be operating on 3 instructions at the same time. So we're executing an instruction while we're decoding the next instruction after that and fetching the next instruction beyond that as well. So we have 3 instructions in that pipeline at the same time. Now, in a modern processor, these pipelines are actually quite lengthy and can have quite a few instructions going on in simultaneously, and that is because they're splitting up all of these phases into ever smaller steps. And you might ask, so how many can we have? Well, the current contemporary Intel processors have up to nearly 200 instructions, as we say, in flight at a given time. So that means that we're not actually running on just this one instruction here. The processor is actually working on up to 200 instructions. This is also made possible because there may actually even be more than one instruction pipeline in a processor. So we'll say there's 1 and then there's 2, and so instructions are running through both pipelines at the same time. The next thing to understand is this concept of speculative execution. And we've talked about that before, where we have something like if C equals 3, then we're going to do something here, else we're going to do something else. Now, it's possible, first before I get to that, in speculative execution, the processor has to go out and fetch the value of C from memory. Now, you may remember that RAM is basically slow compared to the speed of the processor. So what we actually try to do is we try to load values into the processor's cache memory, which we can access very quickly. Now, in order to speed up some things like this, the processor sometimes makes a guess as to what the value of C should be. And it does that based on what it's seen recently in the program execution. That means it's possible to actually train the processor to think that if C equals 3 is true, then it should start doing this. Even though it doesn't have the value of C in memory currently, it will actually go ahead and guess. Okay, C is 3, we'll go ahead and start executing this code. Meanwhile, it's sending a request out to RAM to give us the value of C, and it's also down in the pipeline now, running through a number of instructions, and eventually this value gets stored back into the cache. We now have the value of C. The processor now sees the value of C up here and says, oops, we made the wrong decision. C was not equal to 3. C was actually equal to, say, 4. And we should have been doing this code instead. So what happens next is the processor has to reverse course. It actually has to undo all of the work it has done, then go back and now execute the proper section of code. Now, normally when the processor does this, it completely cleans up after itself, and so the program is always going to have the correct result. The things that were changed here are all reversed and backed out. Now, there's a problem that can occur if the program is set up in a very special way. I'm going to adapt this from the SPECTRE attack paper, so it's not going to be quite the same, and this may not even work exactly as though they have done it, but I think it'll be easier to understand this way. We're going to have the concept of something called array 1, where an array is something in memory, okay, where we have a number of elements of things in memory. If in App Inventor, if you've used a list, say our list has 10 items, then each element in that list would be like an element in an array. We're also going to have a variable called x, and x could have a value like in arrays in this particular language are 0, the index is 0, 1, 2, 3, 4, whereas in App Inventor this actually starts with 1 rather than 0. Not a big point here, but just a minor issue. But what happens, however, if we set x to, say, 10? Well, then we're going to be actually accessing something off the end of that memory that we don't really have access to. And so what we try to do is prevent that from happening in our programs. We're also going to set up a second array that will be used as part of our attack mechanism. And so it doesn't really matter what that is, it's just going to have some values over here where things can be stored. And we're also going to have a variable k that's going to hold a byte of data. Now, what we're going to do here is we're going to write some code that will be speculatively executed. So we're going to say if x is less than array1 size, where array1 size has been defined as the number of elements in this array. So if it's less than that, then we're going to have a little bit of code that executes. And I'm going to say k equals array1, and it will be indexed by x. Next up, we're going to make a reference to our other array, array2, and we're going to index that by k times 256. Why this is times 256 isn't important for what we're doing right at the moment. Now, what's going to happen here at this point is, let's take a look at how this code operates. We're first going to train the processor to think that x is less than array 1 size, because we've done this code before or similar code, so we've trained it to make a guess. But in actual fact, x is going to be equal to 10. But it doesn't know that yet, because we've also set it up so that array 1 size is located out in RAM. And as you know, it's going to take a while to get that value. So the processor is going to guess. It's going to guess this is true because it's been true each time we've been looking at this or similar code in the recent past. So it's going to start executing this code down here. As it goes through this, x of course is now off the end of this array 1, so it's going to actually reference some memory it shouldn't have access to. It's going to store that in our variable k. Then we're going to reference our array 2. It doesn't really matter what values we're putting here, because what we're really doing is we're actually going out and fetching values. In this case, the value at array 1x is going to be, I'm going to write this the other direction, is going to be loaded into the cache RAM on the processor. Secondly, we're also going to reference array 2. Now, while it's doing this, it's also going out to RAM to get that value. About this time, however, this array 1 size value is coming back into the processor. And all of a sudden it realizes, oh my goodness, 10 was actually too big for this. We should not have run this code. So it's now going to reverse course to back out of the code that is executed. By the time we're finished here, k and y don't actually have any valid values anymore, because we've reversed that, we've undone what we've completed, and now the system is going to say, aha, x was actually greater than array 1 size, so we should go do the else part of this and continue on our way. Now, at this point, as we said, we don't know what the values k or y are. They were thrown away when we reversed out of it. Now, I've added two statements after we've reversed here to show that the value array1x has been stored in cache. Also, the reference to array 2, k times 256, was also stored in cache. Because these values are in cache, access to them will be very fast, and that turns out to be the trick to determine what the value of k is that we have read from the memory that we should not have had access to. Next up in our program, we can make a reference to array 2. Sorry for that little ugliness there. And we're going to reference it as n times 256, and n is going to be assigned a value. In the special case, when n equals the k that we had used up here, we're going to be referencing the same location that was referenced here in the cache memory. So at that particular point in time, because this is going to be referencing a value that's stored in cache, our reference will be very, very fast. On the other hand, if we reference a value of k, or rather of n, that is not equal to k, it will not be stored in cache, so it's going to cause a cache miss, and it means that it's going to have to go out to RAM and attempt to read that, so we're going to have to wait. That's going to be time consuming. Now, by looking at our timing here, if we're able to read the value quickly, we know that we've identified the value of k. For values that read in very slowly, then we do not have the value k. So this is what the SPECTRE attack is doing. It's using speculative execution to trick the system into reading access to memory it should not have access to. It loads those values into cache. Then it discovers it's made a mistake, so it backs everything up, but those values still remain in the cache memory. With this clever programming here, we go through and look at the values that are stored. And if we're able to read the value very quickly for that special case of when n is equal to the value of that memory byte, then we know that that was the location in memory because the cache is very fast here. We're able to pull up that value and identify the value k. So through this, the program can actually read out, ultimately, all memory. And therein lies the security problem. There isn't an easy way to solve that in speculative execution.